Okay, welcome to 168. We'll be talking about 3D and 2D finite element analysis today as applied to structural mechanics problems. We talked about the basic steps in finite elements, but now we'll apply those steps to structural mechanics problems in 2D and 3D. I'll start with 3D first, then we'll move to 2D. But the goal is determining how the structure deforms upon when it's loaded by pressures or body forces or traction loads, and determine whether the structure will break under operational conditions. We want to make sure that structure does not break, right? That's the goal. To do this, I think we need to. So we're talking about formulating the strong form of the problem, the partial differential equation, taking that strong form, determining the residual function, making that residual function orthogonal to the space of weight functions, making a weighted residual out of that, and then weakening the continuity requirements to develop the weak form. We weaken the continuity requirements to be able to have to not satisfy all the boundary conditions, essential and natural, but we're also doing it to reduce the order of differentiation. That's very important to us. And then once we get to the weak form, we go to the weak form Galerkin, the approximation method, and then we apply the approximation method by selecting the approximation function so it's sufficiently differentiable so that it is continuous, so that it satisfies the essential boundary conditions of the problem. And then we'll select the weight functions to be the shape functions and make the error orthogonal to each of the shape functions or the basis functions. In weak form Galerkin, there are the phi's. In finite elements, there are the shape functions n. Excellent. And then from there, I have formulated the element formulation. We found that when we formulate the elements, it's very painful to calculate all the shape functions for every single element, but what if in the integration over an element can be complicated? So why not just come up with an approach where everything gets mapped to either a square or regular triangle or a shape that everything is standard. I calculate everything in that standard geometry, and that helps because the shape functions are the same, the integration scheme is the same, the derivatives of these shape functions are the same for every element. And what I've done is I've decoupled the geometry from the problem, and I track the geometry using the Jacobian. Is that clear? By decoupling these two, now every element will have a Jacobian, and now I can just solve the partial differential equation over a standard element. And what I will do next is assemble the system together. Once I assemble the systems together, I apply the loads, I apply the boundary conditions. Now I'm able to now determine the stresses, strains, displacements, and so forth. Although we haven't done that yet, we did it for heat transfer where we determine the temperatures. Is that correct? Okay. So if I summarize this slide for you, so for the type of elements you can encounter in structural mechanics problems, and even heat transfer, will be one-dimensional, such as lines, rods, beams, trusses, frames. We've covered this extensively. Two-dimensional problems, you can discretize the domain into triangles and squares or quadrilaterals. And we covered these two in heat transfer, and I showed you higher order interpolation as well, how to have more accuracy by adding mid-nodes to these elements. We also have three-dimensional elements, and these three-dimensional elements can be either tetrahedrons or hexahedrals. Abaqus has another one called the wedge element, which is not really very accurate. Okay. The type of elements that you see here encompasses one-dimensional, two-dimensional, and three-dimensional. In many of the problems I work on, I'll be either doing two-dimensional, well, I'll do all of them. One-dimensional, two-dimensional, three-dimensional. But you'll be using this more extensively when you go to industry. And shell elements, which I'll cover on Thursday. With 3D finite elements, the idea is that you'll use hexahedral elements to discretize the domain. You have a CAD model. You discretize that domain. What you're really doing is discretizing the domain into elements that you can then map to standard-looking elements, which you can now solve the partial differential equation. Then you can assemble everything together, apply the loads, the boundary conditions, and then you will get the stresses of the system. In this case, there's two competing stress concentrations. There's one at the fillet radii, if I were to apply a load this way. And there's also a stress concentration from the hull. It turns out that in this particular problem, the stress concentration from the fillet radii is much more important than the stress concentration at the hull. In another problem, you can have an impeller for an engine rotating at high speeds, and you can determine, upon loading of this impeller, you can determine the stresses and the strain fields of this impeller and determine whether that structure will fail due to maybe evaluating high cycle fatigue, low cycle fatigue, and so forth. I could also have another problem where I have a pump on an engine and I want to determine the stresses due to the vibrational environments, the pressure distribution, and so forth. So we can use three-dimensional finite elements for a lot of different reasons, many different applications. Just to remind you, in a 3D finite element analysis, the stress state is three-dimensional in nature, and you have 6 independent stresses. That the diagonal terms are the stresses that act on the cube and act to expand the cube in all directions, while the off-diagonal terms represent the shear stresses acting on that cube, which will act to distort the cube, and will impart the shear stresses into the part. You also have the strain field. These strains are as a function of displacements, and these strains right here are the normal strains, and these normal strains act to also expand the cube, while the shear strains act to distort the cube, and so they actually represent the change in angle, this displacement field. We covered this in lecture number 4. Please go back and re-review. This is a summary of that lecture. As you can see here, there's 6 strains, 6 stresses, and we have 3 unknowns, which are the displacements U, V, and W. So as you can see, at every corner in a 3-dimensional problem, how many degrees of freedom I have? 3, U, V, and W. I need to find U, V, and W, and you can imagine it will become computationally expensive really quickly, right, in a 3-dimensional problem. Although I have learned my lesson, computationally expensive for you and I 15 years ago may mean something else. Computationally expensive now means something else, because now we can solve larger problems, right? And so if this video is going to be watched 10 years from now, they may be laughing at us. Maybe they can do millions and millions of degrees of millions of degrees of freedom. Who knows what they can do later on, right? So what I've learned, my lesson learned, is that computationally expensive is a loaded term and that evolves over time, right? So what I could do back 15 years ago now is a piece of cake. It's really quick to do, okay? So take computational expense with quotes, because that meaning changes over time, what you can tackle during that time. Okay, we also covered that in a problem, I apply traction forces, body forces, acceleration, and why not keep the acceleration forces? You guys know how to tackle transient problems now, so we'll just keep that there. And we have 3 equilibrium equations. They're dynamic equilibrium equations. And you can determine now from these 3 equations, given the stresses, given the strains and the displacements, and the relationships between stress and strain, perhaps we can determine the solution to the problem. And you can see it's highly coupled. It's not a quick, you cannot really do it by hand really quick. For a composite material, which I already covered in lecture number 4. Please review that again. You have several engineering constants that define the constitutive matrix, how the strain relates to the stresses. And we covered that these materials which have directionality, for example, EXX, EYY, those are the in-plane directions of the composite. So if I have a lamina, okay, a lamina, EXX will be along the fiber direction. EYY is transverse to the fiber direction, so in this direction instead. EZZ will be transverse direction, so the modulus measured this way across a ply. So if you have a bunch of plies stacked up, basically that direction. And then the shear modulus are also going to be directional, and they could be different from each other in a composite lamina. Okay, so I can relate stress to strain, and for an isotropic material, we can simplify it also into this relationship right here. This relates stress to strain in an isotropic material where, for example, aluminum you only have to define modulus and Poisson ratio. With that two pieces of data, you can get the relationship of stress and strain. So now this is the full picture of a 3D elasticity. I covered this in lecture 4, but we're covering this again in case you've forgotten some of the little details here. But you can see that the stress have 3 equilibrium equations, 6 strain displacement relationships, 6 equations in Hooke's law. Combine all these things together, and what you really have is a set of 15 equations, 15 unknowns, which I can solve now. But what you can do, though, is you can bring it down to 3 equations, 3 unknowns. And to do that, what we need to do is that we have these 3 equations, right? So I can write these 3. Now, it's very convenient to write everything in matrix form, because if I can write in matrix form, I can quickly implement finite elements, right? So what we've done here is taken these derivatives and put them in this manner here. Okay, if you multiply the first row times the first column, you will get the first equation. Okay, so it will work out. The second row times the column there will give you that equation, and the third row times that column will give you that equation. So you have 3 equations, and these derivatives I put in here logically. So when I did these multiplications, it works out, and I get that governing equation. I'm going to call this L transpose, this whole thing L transpose. And I'll call this stress vector sigma bold, and the body forces B bold. We can also add accelerations. You guys know how to tackle that. Rho A double dot, and so we can put that here as well, which I'll do in the next slide. We also have 6 strain displacement relationships. The strains are related to the displacements, and if you go back to the definition of strains relative to displacements, you will see that we'll get it correctly. So if I took this L transpose and transposed it, I will get L, which is a 6 by 3 matrix. And what you see here is if I multiply this row by that column, I get the derivative of u respect to x equals epsilon xx, which is correct. That's what I get. When I take the second row, I multiply that second row by this column, I get the derivative of v respect to y, I get epsilon yy, which is correct. That's what we found. I can also do the one for z, and I get the correct answer here for strain. I can also do shears, and you will see the derivative of u respect to z plus the derivative of w respect to x gives you epsilon xz. You will be able to see that this multiplies correctly. You should try it at home so that you can kind of understand that this does work out. Bottom line, this matrix, by coincidence, and actually it's not coincidence, that matrix is the same matrix as this, but it's transpose. Okay? And we're going to take advantage of that. We also have this full constitutive behavior for 3D, which is isotropic here, but you can make it composite. You can make all these, you can use a fully populated composite material given here. You know, so if you're working with composites, you can fully populate this, and Abaqus can handle it. So the way Abaqus handles this matrix is that you define, or Nastran, Nastran is a Mat 9 card, And then in Abaqus is on the materials, you will use engineering constants. And then you can define the 9 different constants for the composite. And that can be done very, very quickly. Okay? So this matrix can be defined either for isotropic or composites, no problem. And you can see here is a 6 by 6. It relates stress to strain. Now, with all this information, and I want you to kind of memorize this very quick. I'm going to call this L transpose sigma plus B. And then L times U is epsilon, so I'm going to call this L, all of that. Okay? And then I'll call this sigma equals C times epsilon. And these are all matrices. They're all matrices. So in essence, what I really have is these 3 equations, and I want to write that in terms of strains, displacements, because I want to solve for the 3 displacements. And if I know the displacements, I know the strains. If I know the strains, I know the stresses. So the goal is first get the strains. And so to do that, I realize that sigma is C times epsilon, right? Now, the C is 6 by 6. It's huge. I don't want to write that again. The whole point of finite elements is that you don't have to write these things again. You're basically using these matrices. Epsilon is a strain vector, but epsilon is also L times U. You agree? So then I can substitute this stress onto this equation, and I get L transpose C L U plus B rho times U double dot. How many equations I have here now? I have 3 equations, and the only unknown here, I know everything. The only thing I don't know is the displacements used. So I have 3 equations, 3 unknowns. Now to solve that, it will be highly coupled, it will be very complex, but I'll show you how we do it with finite elements, because that's the way that you can actually do it successfully. And L is given here if you've forgotten, okay? Any questions? No questions? That's yours? You can model a composite ply, a single ply, with this approach, with 3D elements. In each ply, you specify the orientation and the engineering constants, the 9 engineering constants. So then you model every single row with each row is 1 ply of elements, and you can do that. Okay, but it's computationally expensive, so you go to shell elements, which I'll cover the next lecture. Okay, so with that said, we're ready. That's my governing equation. This is it, right here. 3 equations. Don't forget, there's 3 equations here, 3 unknowns. Okay. And with that information, I'm ready now to develop the weak form. Well, actually, I didn't do it using the weak form. I decided I'll cover the 3D using total potential energy, and I'll do 2D using the weak form. But you will get the same answer if I did the weak form versus the total potential energy. So I think it's valuable for us to do this with total potential energy, because we haven't used this recently. With total potential energy, you're going to have to use the Riley-Ritz approach because you have a functional now. But at the end, you'll get the same answers. Everything's going to work out very nicely. But this is total potential energy. This is strain energy for 3-dimensional problems. if you remember for the 1D problem, all of these were 0, right? Okay. For Timoshenko, this was non-zero and that was non-zero, right? But now we're talking about 3D, so all of them are active, they're present. The body forces now have a potential energy that go with them, but not just in one direction, but other directions as well. You also have the tractions. They're acting on the boundary of the body. Okay. You also have point loads that you could have that are also acting on the body. So in a very compact form, we can put this in a stress vector and a strain vector, and what I get is 1/2 sigma bold transpose times epsilon bold minus b bold, which is the body forces, times u bold. I can put that in a very compact form to get the total potential energy. I could also add the kinetic energy, but I do that later. That's okay. Minus T bold times U bold times Q bold, U bold. So this Q bold, U bold is this one here. And then T bold, U bold is this one's here. Okay. Any questions? You agree that the top simplifies to the bottom in a compact form? So basically this is strain energy stored in the body. These are the potential energy due to the loads. These together constitute the total potential energy of the system. Okay. And what I'm about to do is going to take us really quickly to the final answer that we need, which is the element formulation for a 3D body. For a 3D body, let's take a general situation, because you have so many different kinds of elements in 3D. It's just better to take a general situation, okay? So I could have a tetrahedron which has 4 nodes. I could have a hex which has 8 nodes. I can take a second order tet which has 10 nodes. I can take a second order hex which has either 20 nodes or 27 nodes. You can imagine how quickly this becomes very unwieldy. So why we don't keep track of everything in a simple manner, I want you to check with me that this is true. So if this is my displacement u, v, and w, and q constitutes my displacement field for every, so these are for my first node, the displacements are u1, v1, w1. For the second node, I have u2, v2, w2. For my third node, I have u3, v3, w3. So I have 3 unknowns per node, and I'm going to keep this open. I'm going to say m for now, which means I could have m nodes. I could have 10 nodes, 20 nodes, 27 nodes. I don't care. The formulation is going to look very similar. So why not just keep that open, right? And so we can, in a very generic manner, general manner, show you how to develop the element formulation. So this is the unknowns for the m node. Okay, and so if I find what u is, right, I put this matrix in this format for a reason. I put some zeros in between, and so the reason this is done is so you keep everything in a compact fashion. So let's see, for example, if I multiply the first row times the first column, which is really over there, I have n1 times u1, you agree? Plus 0 times v1, agree? Plus 0 times w1, agree? Plus n2 times u2, plus 0 times v, plus 0 times w. So you can see that n1 times u1 plus n2 times u2 plus n3 times u3, etc., nm plus um. So I have a bunch of shape functions for just the displacement u. Okay? That's no different from anything we've done for example when we cover heat transfer. We only had, the only difference there is that I only had 1 unknown per node, which was temperature. But now I have 3 at every node, so I have to keep track of that. More work. Second row there, you can see I've shifted everything 1 to the right, and these are zeros. And that's done on purpose, so that when I multiply this second row times this column, that when I multiply this, I get 0 times that, n1 times v1. See that? Times 0 times w1. So now again, anything that has v's are active now. Everything else is not active. So that way, my displacement v, my vertical displacement v, or along the y-axis, that displacement is interpolated with the nodal values that are basically V1, V2, V3, and so forth.
So the shape function N1 to Nm are different in each row?
The shape functions in one are the same for all of them. You're going to use the same shape functions for U, V, and W. Okay. For W the same way, they're shifted more to the right. So when I multiply this row times that column, it coincides so that I only have N1 times W1, N2 times W2, and so forth. It's done on purpose.
UVW represents the displacement of the element, right? So
UV and W represents the displacements at any point inside that element.
So what does it mean that U is the sum of all the individual U's of each node as opposed to like an average?
We're not doing average. We're interpolating the displacements inside that cube or that hexahedral, right? We're interpolating that displacement using the nodal values and the interpolation function that go along with them.
So
That's basically our approximation function, similar to heat transfer problems, right? Where we had temperature inside the in our case was a rectangle, right? You took the temperature inside the rectangle and you interpolated that using the nodal quantities, T1 times N1 plus T2 times N2 plus T3 times N3 plus T4 times N4. And the shape functions have to satisfy the Kronecker delta property and partition unity. These shape functions constituted the basis functions, and in essence what you have there is approximation function. Isn't this U equals N1 times U1 plus N2 times U2 basically approximation function? Just like Riley-Ritz. You have U equals phi times unknown coefficients. Now your unknown coefficients are the unknown quantities of the knowns, which are U1, U2, U3, U4, and then your shape functions become the basis functions in weak from Galerkin or Riley-Ritz.
So can I have the shape function the same for U and V? Let's say U is in axial direction and V is transverse. The shape function will always be different like that?
The shape functions, the actual shape functions for U, V, and W at each node will be the same. There's no reason why to not make them the same. Right?
And also for cube elements, here are
For what?
cube.
For a cube.
Yes.
Yeah.
So there are 8.
8. So M in this example will be 8.
Yeah.
For the cube, it will be M equals 8. For a tetrahedron, M will be 4. For a second order tetrahedron, which will be 10 nodes, will be M equals 10. Right?
Yeah.
So let's take the example of tetrahedron. How many nodes do you have for a tetrahedron? You have 4 nodes, right? In 3D. I'll show you a picture later. So how many degrees of freedom you have? 12. So one element has 12. So your stiffness matrix has to be 12 by 12. We're not giving you that in the file. Okay? Because you'll spend more time writing these matrices than doing the work. Right? As you're experiencing right now for the heat transfer problem. Sorry, you have to go through the pain once. You don't have to do it again. Okay? Hold on, tight. Just 2 more weeks. You'll be done. Okay? All right, so I'm ready. I'm ready to plug in my approximation function, which is this one. This is my approximation function. These are my basis functions, and these are the unknown coefficients in Riley-Ritz. So I'm ready. I'll plug this in to my total potential energy. And if you recall, this was stress, wasn't it? So let's go back so you remember what we had there. We had stress times epsilon. So let's cover that one. And now we need to notice, don't you agree that L times U is strain? Right? And if you're forgetting where that came from a couple of slides back, which is right here. LU equals epsilon. So we cover that one. Okay? And so, do you agree that LU equals epsilon, and therefore C times epsilon is stress? Do you agree? Yeah? So all I've done is expanded this so that stress is C times LU. And then remember, this was strain, so that's LU. Yeah? And so now I have the rest of it, which is just U transpose B, U transpose T, U transpose Q. Now I'm ready to substitute my approximation function. I'm going to do that now. And when I do that now, I realize that U bold, which is this matrix, is N bold times Q bold. So U bold equals N bold times Q bold. That is my approximation function right here. Just that expression right there is my approximation function. So anytime I see U here, I'm plugging N times Q. And Q is the nodal unknowns. These are my unknown coefficients. And N is my basis functions in Rayleigh Ritz or Wigform-Galerkin. And when I do that, I get N bold times Q. And then I also get N bold times Q right there. And then for U, I get N bold times Q, but because I have transpose, it gets switched around when I apply it. And then I get N bold times Q there, and it's transpose, so I get all that switched there. Same here. You got switched there. Any questions? You follow it? So now I'm ready to apply the transpose here. But I'll do it very carefully. I'll apply the transpose on C. So the C comes in the front now. But C transpose is symmetric. Don't you agree? C transpose equals C. It doesn't change. The stiffness matrix is symmetric. Okay, so that's why you don't see a transpose there anymore. You agree that when I apply transpose to Q, Q comes in the front. And if I apply transpose to L times N, it just stays like that. Right? So all I've done is apply the transpose really quickly. Everything else stays the same. Okay? Any questions on this? Any questions on this? These are all matrices. They're all known. This L here is fully known. The N is this one here. C is fully known as the matrix, the stiffness matrix of the system. Q is a nodal unknowns. That's what I'm trying to solve for. Okay? But right now I have total potential energy. Now I can make Ln, I can call it something else. I'll call it B bold, so I don't have to keep writing Ln. It'll be nicer to write it just as B bold from now on, and I don't have to deal with writing Ln. Especially, it does not look very pretty, that bottom equation. So we'll take it to the next level. Let's see what B is, this Ln. Let's see what that is. That's basically L, which is this one here, times N. Okay? So what I'm doing here is, this L is a differential operator. So I take the first row times this column, and I get derivative of N1 respect to X. That's really what I get. And I can continue getting these derivatives. And what I'll get, this is a 6 by 3, you agree? And this is a 3 by M, or 3 by 3M. Right? Because I have M nodes, I have 3 degrees of freedom per node. Then the length of this is 3m. The height here is 3. So I have 6 by 3 times 3 times 3m. Okay? And so I'm ready. So I can substitute for Ln, I can make it B bold and just track it there. Okay? This is what I get right now so far. Any questions? You agree that the shape function at the node of interest is 1 and everywhere else is 0? So therefore this will be either 1 or 0 in essence. Okay? So I'm ready to make it a little bit prettier. I'll put the Q. Q does not depend on volume, you agree? These are the unknown coefficients. So I'll put the Q bold ahead there, this Q ahead there, so I have this integral to calculate. Minus Q bold transpose, I put it again outside the integral. N transpose B dV minus Q transpose outside the integral again. And then this N transpose is either 1 or 0. Basically you get this. Okay. Q are the nodal unknown coefficients. The nodal unknowns that we don't know. U1, V1, W1 at node 1. U2, V2, W2 at node 2, and so forth. Okay. Now I can minimize the total potential energy with respect to the nodal unknown coefficients using Rayleigh Ritz. So the derivative of pi respect to Q bold is going to result in a system of 3m equations. Okay, so the matrix, the final matrix will be 3m times 3m. M is the number of nodes. And basically, you just take this 1/2 Q transpose away, this Q transpose away, this Q transpose away, and you get the final equation here. That is the element formulation you're using Ryder-Ritz. We've applied this a few times now, so you should be quite aware of what we're talking about here. If not, please talk to me. We can add the kinetic energy. I could have added it right there. But I know how it's going to look, so I just added it here. So it's rho n transpose n dv q double dot. But we could have added it very nicely here as another term. It will not be too complicated to do because it will be just integral of volume 1/2 rho u dot squared. And then if you minimize that term, you will get this q double dot. But for now, that is what we get. If you have any questions, just talk to me at the end. But there is a dynamic finite element equation for 3D. And for 2D, it's not very different from that. Because for 2D, basically, instead of volume, you have area times the thickness, h, right? So, in essence, I've covered 3D. We've done it. This is as hard as you can get. I mean, I don't know how harder you can get with this equation, okay? N is fully known. These are the metrics of shape functions. This is B bold. You can calculate that. You can calculate C bold. You can calculate all these things. You're ready now to now, you're not ready because this is for regular hexahedral elements. So. But what if every hexahedral had different shape? Then I have to do this for every single element. Well, let's try to decouple the element geometry, map that out to a cube. It would be really nice if everything looked like a cube. If I can make it look like a cube, then I'll have even more success in trying to solve these equations. These I can integrate over that cube more easily. I can also, the shape functions will be the same for all of them, and so forth. So I'm ready to now apply isoparametric formulation. What I really want to do is convert that as d volume. So it's dip c d eta d what do you call it? Zeta, yeah. Dip c d eta d zeta. And so then I have this dv, and then I have the determinant of the Jacobian. So I can turn that volume into that. Now my integrals go from -1 to 1. So I have triple integral from -1 to 1 there. And I have this triple integral -1 to 1. I have this triple integral -1 to 1. This is a surface integral for the traction forces you apply. The Jacobian can be found as this equation. So if I need to calculate this determinant, I have to find J bold, which is a 3 by 3 now. And then you have derivative of x with respect to c, derivative of y with respect to c, derivative of z with respect to c. So now I have to parameterize what x, y, and z are in c, eta, and zeta coordinates. You agree? I have to do that next. Am I losing you? You're here? It's okay if you're not here. You'll be here eventually. So let's see what's going on. So what I'll do, I'll parameterize x, y, and z so that now the shape functions are in terms of c, eta, and zeta. And I'll use the same shape functions. I'll use the same shape functions. Why not? Use the same shape functions to parameterize x, y, and z, which is the coordinates inside that hexahedral or tetrahedron. And not only that, these are the coordinates of the nodes. And there's triples, right? So these are triplets. x1, y1, z1, x2, y2, z2. These are triplets of values that come together for each node. I need to know the coordinate x, y, and z for every node, right? So the idea is that if I multiply the shape function matrix times its coordinates, I recover the locations in the global system, x, y, z, right? And then so you agree that I know the coordinates of every node in a particular element? Yes, you know it because you constructed the model. And so the software knows these numbers altogether. It knows it. Okay? I know the nodal locations. If I have that, you agree that I know C then? I know all of it? I know the shape functions because I'm hoping the shape functions are the same for every element. So this is known, C bold is known, so I should be able to calculate these derivatives now. I should be able to do that. Because if I have x, y, and z, and they're terms in terms of shape functions, which are in terms of C, eta, and zeta, then I should be able to calculate these derivatives. Okay? So I'm parameterizing the problem. Okay? In this case, I'm looking at a cube, right? So I'm parameterizing everything to a cube. I also need to calculate, I'm going to have to calculate these derivatives at some point. If you remember, these derivatives need to be calculated later on when I have that. Remember that L matrix, L bold matrix? That L bold matrix is a bunch of derivatives with respect to x, y, and z. So I need to calculate this as well. And so we're going to use chain rule. Basically, you can see here that that's chain rule. Derivative of ni raised to c. And I is just 1, 2, 3, 4. So if I have m nodes, right, then I have m shape functions, basically. So derivative of ni respect to c is basically derivative of x respect to c times that, plus derivative of y respect to c times that, respect to z, derivative of z respect to c times that. So in essence, that's my chain rule differentiation, that first row. And second row the same way, third row the same way. You agree that I already know this for sure? I know this from the previous slide. This is what I want to get. I really want to get this. Do you agree that n's are in terms of c, eta, and zeta? So I should be able to determine these derivatives very quickly. I have that. I have this. So I can invert this and I can find these derivatives with respect to x, y, and z, which I'm going to need them. I'm going to need those derivatives. I'll show you where. But let's call this J bold, Jacobian of the element. The inverse of that is given here, and then times this, and these are all known. These I know the shape function, so I should be able to get this. So once I have these calculations, I'm ready to use this information, right? Because if I calculate L times N, which we call B bold, it looks like this, okay? It looks like that. So once I calculate the derivative of Ni in respect to x, now I know this value. That value goes right here. Once I know the derivative of Ni in respect to y, that value goes right here. And then once I know the derivative of Ni in respect to z, that value goes right here. And then same for the other ones, okay? You can calculate those very quickly. These are blocks. So this is for shape function 1. You have to repeat this for 2, 3, 4, 5, all these shape functions. So therefore, B bold becomes B1, B2, B3, up to Bm, depending on how many nodes you have. Okay? That is L bold N. That has not changed. Okay? I don't know if you track, but in essence, what I've done, I calculated so you see this matrix is how big is it? 6 by 3. And then I basically calculate a block, so that's my first block. So 3 by 3. So 6 by 3 times 3 by 3. How much does that give me? 6 by 3. So that's my first block, and that's what I call B1. My next block is B2. Next block is B3. Bm. That's why you see it broken down like that. Because this is a generic block. Every block looks like this. It's just that I changes values 1 through how many shape functions I have. And that's why you see this B1 bold, B2 bold, and so forth. Okay, but each of these has a size that's equal to 6 by 3. 6 by 3, 6 by 3, 6 by 3, 6 by 3. This should be a size equal to 6 by 3m. Okay. So I know the Jacobian. I know this calculation for every shape function. I know B bold completely. They're all in terms of C, eta, and zeta. Now I'm primed to substitute that in here. Now I have B bold, B, because I've calculated that. my dv's are already done. I know the Jacobian, I know the determinant. All my integrals are from -1 to 1. I can use Gauss quadratures to evaluate these integrals. And then I still have to tackle this surface integral, which can be done quite readily. Okay. Any questions on a 3D element formulation? Are you guys following the steps? So the 3D element types, the common element types are the tetrahedron, which is going to have a constant strain throughout that element. The second order tetrahedron, you also have the cube, hexahedral, and then the second order hexahedral. There's two of them in Abaqus. C3D20. So in Abaqus, C3D4, C3D10, C3D8, C3D20, and they also have a version called C3D27, okay, which is computationally expensive, okay. The shape functions, let's take a few minutes break. Okay, so we'll continue here. But the hexahedral shape functions, they're very difficult to write one by one. So you can write it in very compact form in this manner, 1/8. So each shape function is written as 1/8. 1 plus c, 1 plus eta, 1 plus zeta. And if ci and eta I and zeta I are given this table for the 8 nodes. So that's for just a cube. And so if you substitute this one for the first shape function, what you really get is 1 minus c, 1 minus eta, 1 minus zeta. So that's your first shape function. And then you can then look at the other shape functions, and they're very quickly, you can get them by just applying this table. Abaqus, in their theory manual, gives you all 8 shape functions. They write it down one by one. Okay, but you guys go back and verify that what I have here is correct. Then you have something called the serendipity element, C3D20 element. Abaqus also gives you then a theory manual. Perhaps if we have more time, I'll pull it up so you can see. I wrote it in compact form. And the shape function for the 8 corner nodes are given here. So 1, 2, 3, 4, 5, 6, 7, 8. Those are given by these shape functions. And then you have 9, 11, 17, 19, which are for these edges here, the ones at the bottom. Okay. Then you have another set of shape functions that look like 10, 12, 18, and 20. Those are for the other cross-section, and then these ones are for the next cross-section. So these are very, very expensive element. We're talking about 60 or so, 60 degrees of freedom per element, but very, very, it's accurate. You can't get more accurate than that.
How does the first shape function work? For example, for n1, how does that go to 0?
Yeah, you just go to this table.
What about psi?
Yeah, so this table gives you the value of Ci, eta I, and zeta I. So you plug in the values for node 1, minus 1, minus 1, minus 1. Plug it in there.
How about the psi itself, the psi I? Because there's 2
The psi, eta, and zeta are the coordinates of the cube, right? The shape functions. The shape functions have to have a coordinate, right? It goes from minus 1 to 1, the cube. I didn't draw the cube here, but the Abaqus manual has a cube given there. Any questions on that? I'm not going to make you memorize this. It's not happening. I can make you memorize that one. That should be easy. A tetrahedral element is a C3D4 element. The shape functions are very quick. You can write them out. 1 minus r minus s minus t, r, s, t. And those are the coordinates of the element. So there you go. And the node locations for element, so for element 1, sorry, lost my train here. The tetrahedral element, C3D4, the nodal locations are given here for the 4 nodes. Okay, and then since you can also use the same table for the 10 noded element. These are the shape functions. There are 10 shape functions. You'll have basically an additional degree of freedom per edge, and whenever you see Q, those are the additional shape functions you need to make that tetrahedral element happen, this 10 node element happen. Okay, very, very good element too for 3D problems. The tetrahedron here, the linear tetrahedron, not as good. Okay, because this is a constant strain element. Okay, this is a linear. This gives you a linear distribution of strain across the element, so it's very good, very good. Quadratic interpolation too. Okay, quadratic interpolation across every edge.
That's like still a linear strain.
Yeah. Really good element. This one, not so much. It's constant strain throughout the element. Okay. But you can see the computational expense really quick. So 4 times 3, 12 degrees of freedom. How many degrees of freedom here? 30. Really quick. It increases the amount of degrees of freedom. Let's compare 2 types of elements. So these are closed form solution for a bar subject to bending loading. For this geometry, R over D, the fitted radius to this diameter is about 0.1. I can go and calculate the stress concentration is 1.78. If I were to use finite elements for C3D8, I get about 1.68. Okay, and then if I use tetrahedral elements, second order, 1.72. If I use linear, it's like 1.4, 1.3. Not very good. Okay? But very close to that answer. So just comparing the two for now, but nothing spectacular, just giving you a comparison there. Okay. Now do this by hand for the final exam. I don't think you want to do that. Okay. Right? Just use Abaqus. But I think everybody now knows what Abaqus is doing internally. Do you agree? What is it doing? Tell me. What is it doing here? What is it doing here? I have a domain. You discretize the domain yourself because in Abaqus you'll mesh it, right? When you measure it, what you're doing, you're actually telling Abaqus how to discretize that domain, aren't you? What is Abaqus doing now? Well, Abaqus has the weak forms for each of these physics problems, heat transfer, solid mechanics, and then Abaqus already has the shape functions, all of them. They're in a theory manual. I'll open it up so you can see they're all there. So it already has all this embedded in the code, and it's basically using this information. You don't have to do the assembly. Abaqus is doing that. You apply the laws, the boundary conditions, and Abaqus solves the linear system of equations. Okay. It is very possible for every single one of you to write your own code. Okay, your own finite element code. You don't have to do that. You can use what the Abaqus Student Edition Forever, or just buy it. It's 30 grand maybe per year. I don't know how much, but it's expensive, right? But there are other codes online. They're open source. Open source codes that you can use that try to replicate Abaqus. If you're going to do research, like a PhD in finite elements, sometimes having your own code is useful, because then you can do things you can do there that you may not be able to do here very quickly. I may show you when we cover fracture. I wrote a user element that basically models fracture, right? But I'll show you that I use shape functions, I use Gaussian quadrature, I use all this stuff we're talking about. There's no difference. Okay, the only thing I did different in my code was the constitutive law was different for my problem. I was trying to look at fractures, so I came up with the springs that break. And the constitutive law was different. But otherwise, the formulation isn't the formulation about the same over and over and over? I mean, we did heat transfer. You did a cable problem. These problems have the same steps. Okay? You have to do isoparametric, right? To make all the elements behave the same way, or map them to a region that's regular for all the elements, But in essence, that is the concept of finite elements. That's what we're trying to do, solve a very complicated partial differential equation for a complicated domain, but we simplify the problem. For 2D elasticity, which I think is worth going through, there's two equations only. The only unknowns are U and V. Now this looks way simpler now. We're talking about a 2 by 3 now. So the first row times that. Actually, I think I have a problem here. No, that's correct. That's my first equation. And then my second equation is that. So I do get it. So that's right. I use the partial here, but you can use L. Okay. Just for consistency, maybe we fix that and make it L. If I take the transpose of this and multiply by U and V, there's only two unknowns now for 2D. Then I get LU. Epsilon is the same thing as that, but transpose 3 by 2. The constitutive law changes depending upon whether you're working on plane stress or plane strain. I'll cover what plane stress is versus plane strain. But in essence, in my book, I go into extensive detail on plane stress versus plane strain as well. But you guys can see the constitutive law here is 3 by 3. I can now formulate. I have two equations here. That's my strong form. I can substitute what sigma is, which is C times epsilon. C times epsilon is C times L times U, right? Substitute that there, and then I get two equations here, and I give you the size of the matrices. Very clear here. And that's your L bold. Okay. So there are different types of elements. I'll cover axisymmetric next Thursday. But you have plane stress versus plane strain, in essence, for 2D elements. For plane stress, those plane stress usually works well when the structure is a thin, flat plate, so a 2D plate, say, where all the loads are in plane. Okay, so the loads are just applied in plane of that plate. Okay. The through thickness stresses are negligible. When the through thickness stresses are not negligible, and the loads are out of plane, you have to use shell elements, which we'll also cover next. Okay? And the constitutive law looks like this. For plane strain, the loading also happens in a 2D direction, but the 2D plane, the 2D plane, the planes are far apart from one end to another. So it's very thick, okay, almost infinite in one direction. Every 2D section looks exactly the same. The structure does not deflect like a beam. Supports are the same along the length. An example is, take a pressure vessel and say the pressure vessel is about 20 feet long. But it's about this size, right? Say. I'm just making an example. Well, then I can take that cross section and just model that because it's so long that all the stresses basically, you could basically assume that if I'm looking at stresses in that plane, that there's the same all the way through. Okay. Abaqus has an advanced version of plane strain, which I think you should read about. But it basically, if you have a pencil that's very long, you can model that cross section that's representative of every cross section through a thickness in that long section. But this element in Abaqus called a CP, don't quote me on this, CP4G, I believe, is able to apply CPE4G, that's the element, generalized, G for generalized. You can apply loads at the end. It's incredible. You can apply bending and out-of-plane loading, not just in plane, but also out-of-plane. So they were able to extend that formulation further. Okay. I've used that formulation quite a bit, so just keep that in mind. You can do that. This element here is the CPE4 in Abaqus for quadrilateral, and for plane stress is the CPS4, I believe. Okay. So how we go about this? We have the strong form of the problem. So let's not use Riley-Ritz now. Let's use weak form Galerkin so you can see a different way of doing it. We're going to get the same answer at the end. You know it. That's 3D. Put everything on one side of the equation. That's my residual function. Make that residual function orthogonal to V, the weight function. Now I'm gonna weaken the continuity requirements here. Remember, these L's are differentiator. They're differential operators, right? So that L is this one here. So I'll take one of these guys, and I'm going to shift the order to V. So then what I have is L transpose CL, this an error. We don't want to write U there, right? Or do we? Yeah. We keep the U there. I'm sorry. This is correct. Okay, and so then I'll remove one L transpose, put it there, and now I have just a single order differentiation here, a single order differentiation here, plus, minus, there's an N there because the boundary, right, for an area, right, section is what? A line element surrounding that boundary. So I need to know the normal at any point there. This is just a fancy way of doing Gauss theorem or diversion theorem. I'm just doing it in a different way. So we integrated parts to weaken the continuity requirements. And so what I have here is this multiplied by that goes back into the integral, which is what you see here. So this times that. And then we have this term which goes into your boundary term. Okay. So V, CLU times V times N bold. So that's what you have there. Now, this one is interesting. Without looking at what I wrote, what is L times U? Strain. What is C times strain? Stress. What is stress dot N? The traction forces. So those are the tractions acting on the boundary. So automatically, by me developing the weak form, I came up with the boundary term automatically. And now in the previous lecture for heat transfer, I divided that surface integral. I didn't do it here. I divided that surface integral into two. One where essential boundary conditions are specified, one where natural boundary conditions are specified. We already showed you in the previous lecture that the ones that where essential boundary conditions are specified will vanish because V will be selected as the basis functions, and the basis functions vanish at the location where essential boundary conditions are specified. Okay? So that's why I didn't go through that exercise, because we covered that in heat transfer. I don't want to repeat that here. But I repeated it verbally, and hopefully you can remember that. If you take a more advanced course, I can show you by first principle that this is actually an equation that is true. And I covered that maybe lecture number 4. Okay? But in a more advanced course, this is called Cauchy's relationship. Okay? Knowing the stresses inside the boundary, knowing the normal, you know how that traction relates to the stresses at the boundary. So now this is the weak form of the problem. L is given by that, but that is the weak form of the problem. And I'm ready to now apply weak form Galerkin as the approximation method. Oh, and H is the thickness of the plate. Okay? Or if it's plane strain, the thickness in the Z direction. I now apply again the principles of weak form Galerkin. I did it before Riley-Ritz. What I'm going to do now is a little bit simpler. It's only 2 rows now because it's just UMV, only 2 unknowns per node. And so then I'll take the shape functions, N1, N2, N3. You know, so I'll shift it to the right ones, so that when I multiply this row times this row, or this column here, it's really a column, that only U1, U2, U3 are active for the first equation. So that's my approximation function for U, is that it be interpolated with the shape functions N1, N2, and so forth, with the nodal unknown quantities U1, U2, U3, and so forth. And the same for V. Okay? So I'm ready to apply weak form Galerkin. Weak form Galerkin, I take my approximation function. Isn't this my approximation function? In weak form Galerkin, what you really had, like if you go back to lecture number -5, wasn't the weak form Galerkin like unknown coefficients times basis functions? And then I'll plug that in, right? This is what we're doing here. I have basis functions times unknown coefficients, and that's what I'll plug into my weak form. And when I do that, I also have to select my basis function, my weight function, to be the basis functions. So I'll make it in transpose. So let me begin. So I did it here. So this is my weak form when I started. For U double dot, I have N bold, Q bold. So that's basically N bold, Q double dot. But then for V, I have N transpose. So that goes there. And then for U, I have N times Q, which is this times that. Okay? And then for V, I'm selecting N transpose. So that's what I have there. Okay? Then for V, I have N transpose. For V, I have N transpose. I'm basically done. And so now, if I were to write this so that the transpose are removed and they're just put together, I get N transpose. You see that? Yeah? Everything else looks like the 3D. I don't know if you remember, but it just looks like 3D, doesn't it? I actually don't see any difference between the 3D.
This can be applied to both
Plane strain and plane stress. Yeah. The only difference is the constitutive law changes. This C changes for plane stress versus plane strain. Yeah? That's the only difference in the two formulations, right? You guys have any questions on that? Now that you learn both methods, total potential energy and weak form Galerkin, I'm very curious to take a survey and see which one you like better. Right? We did it both ways. It's exciting. You took the total potential energy, minimized it, and you got the same answer as when I took the strong form, turned into weak form, and used weak form Galerkin. I got the same answer with both ways. But it will be very interesting to take a survey to say, to see which one you like best. I'm surprised nobody wants to ask which one I like best. You want to know which one I like best? Both. Because with both you get the same answer. So it reinforces my understanding that things should work out, right? I don't have a favorite. That's my answer because I like both. Okay? To remind you that this is what I got, it'll be good to just go a couple of slides back, and I'll show you. This is what we got back there. But everything was d volume, right? Of course. Makes sense. It's 3D, right? For 2D, I'm making the volume be h times dA. That's the difference. Okay, so let's see what happens now with how to deal with the isoparametrization. We still need to make it isoparametric. I did it a little bit different in this second part. I was trying to do things differently so you can have multiple views of the same thing. But the process is the same. What we really want to do is turn this dA into deep C d eta. That's really what we want to do there. These are the coordinates. Do I know the coordinates of the nodes? I know them. So that I can parameterize x and y using the shape functions and the coordinates. From here, if I know the coordinates and I have the shape functions, I can get the Jacobian. I need to calculate these derivatives, right? I have to calculate those derivatives. So to get ready for that, we use chain rule, which is given by these formulas. And I have to invert that so I can calculate derivative with respect to x, derivative with respect to y. I know the Jacobian fully. I know the shape functions as a function of c and eta, so these derivatives can be calculated very quick. So I know this, I know that, I can get these derivatives. And once I get them, then I plug it in here for each of the shape functions. And again, I have blocks here now. They're now only 3 by 2. Okay? And so now the length of this is only 2m. It's not 3m because it's 2D now. I also have turned my weak form into determinant of j, deep C d eta from -1 to 1, double integral. for each of these. And then this is the boundary term that needs to be tackled separately. And we covered that in the heat transfer problem, and today I'll do an example of that. For triangular elements, the limits go a little different, and we use R and S instead. So that's why I wanted to show a slide on that. But the integrals go from 0 to 1 minus S, 0 to 1. Everything else is the same. The formulation is the same. Nothing changes, just the integrals. Okay? Because now it's a triangle. It's not a square from minus 1 to 1 minus 1 to 1. The element types are the following. So you have a triangular element. This is called a constant strain triangle because the strains are constant across the triangle. 2 unknowns per node. That's called also known as the first order triangular element. In Abaqus, C2, don't quote me on this. Actually, can't remember. No, I'm sorry. Yeah, I told you about them. It's CPS3 for plane stress, CPE4 for plane strain. And then second order triangular element, linear strain triangle. Basically, the strains are linear across the element. But second order because you're interpolating quadratically, and you have a mid node there. Okay. Quadrilateral elements, first order quadrilateral element Q4. I don't have it depicted here. It was shown in the previous lecture for heat transfer. It uses bilinear shape functions. And you also could have a second order quadrilateral element, which I covered last week, the serendipity Q8 and the bubble function element Q9. So that was covered in the heat transfer lecture. But here are the degrees of freedom you get for each of those. Solid mechanics example. Let's do an example because I think it's easier, a little bit easier to visualize all these things. Now, I'm not going to do a 3D example. We'll just do a 2D example. I think that's enough. There's a point in time where the amount of work you put in there has diminishing returns, right? So me teaching a 3D example will be, it's just the same. We can cover the same with the 2D example. Is that fine? Okay. I encourage you that if you want me to cover a 3D example, you prepare the PowerPoint for me. Then I can do that, okay? With that said, this is a solid mechanics problem. I'm going to do a shear distribution across this surface. A shear distribution across this surface. This is a domain that looks like this. This is a domain. B equals 3 aluminum. I'm going to put gravity too. Why not? Let's put gravity. What else can we put? We can put acceleration too, but let's not do that. Let's say the thickness is 1 inch. And I'll be covering you had a question about how do I tackle tractions, whether they get mapped, how they get mapped. I still remember your question. We'll cover that a little bit. All right. You follow so far the example, what we're going to do? So step 1 is to discretize the domain. I think I don't want to do 20 elements because it's a PowerPoint, so we'll do 2 elements. What about 2 elements? 1 element here square and 1 element here triangle, okay? So just 2 elements. I think your homework has many more elements.
What do you decide to do? Square, triangle, or 3 triangle? What do you decide which one to do?
Because, so your question is why I selected 2 elements and not 3? The answer is simple. Less work for me. For me to teach you a concept, I don't need 200 elements. I just need 2 elements to teach you the concept.
The answer is different with the same type of elements or different type of elements?
This is so if I were to do this analysis, the answers I will get out of this are inadequate. I really need to have like a large number of elements to really get the behavior correctly. But for illustration purposes, I'm just doing 2 elements. In your homework, problem number 1, which I agree is a little bit painful, but just to remind you, I did that problem also. And I did it in PowerPoint. And I think I had 5 elements, if I can remember. I had 5, you have 4. So you have a little bit better than I did. However, you have to use Gaussian quadrature on that, so that kind of increases the amount of work you have to do, okay? Yeah? Second thing is, well, it's not completely fair. You have elements that don't look cubes. They're like a little bit distorted, right? So, but you have to get some work done, okay, on that. The second problem, I think, is a bunch of triangles, isn't it? But if you look at that problem, almost all those triangles have about the same shape. So when you calculate integrals, they're all going to be very similar to each other. If you number the elements correctly, you number the connectivity in a smart way, you can get it all so it looks the same, except for two triangles in each of the edges. Okay?
Do we need to use isoparametric?
If I was you, I'll use isoparametric because it will simplify all the calculations. You can just use one shape function for everything. The Jacobians will look different. That's it? Now you understand why I did two elements and not three. Less work. But I can teach you the concept. So for element 1, I'm going to use a Q4. And I'm going to use 1, 2, 4, 5. That will be the way I'm going to number them. The IDs 1, 2, and 3, and 4. For the second element, I'm going to use a constant strain triangle, also known as triad 3, or in Abaqus will be CPS 3 or CPE 3. Okay, so then I have this element there. The connectivity, I'm going to choose it to be 3, 4, 2. 3, 4, 2. It doesn't have a fourth node, so X that out. You're going to use this to assemble it. I'll be honest with you, I didn't assemble anything. I just calculated the matrices for... I didn't even calculate the matrices. I just wanted to show you the steps. You guys can do it, okay? For node 1, I have 2 degrees of freedom. These 2 of these, so 1 and 2. For node 2, I have 3 and 4. For node 3, I have 6 and 7. Sorry, for node 4, I have 6 and 7. 5, 7, and 8. 3, 5, and 6, and so forth. Okay, and these are the numbers you're going to use for connectivity. So how you're going to assemble everything together. Is that clear? You guys learned connectivity the first lecture. Just to let you know. So I expect everybody here to be an expert. Okay, so let's just apply the concepts we learned. So I know the coordinates. You agree? I know the shape functions for a quadrilateral element. I gave you those last week. For example, shape function N1 for a quadrilateral element for node 1 is, if I remember correctly, is 1/4 of 1 minus C times 1 minus eta. That was the shape function for node 1. And that was covered in the previous lecture. So these shape functions are known. When I multiply this times C, I will get 3/2, 0, 0, 3/2. That's what I get. J inverse is quick. It's 2/3, basically the inverse of that. And then J determinant is 9/4. Okay. I think that makes sense. Let's see if it makes sense. We can actually make sense out of this. What is the area of a standard element that I'm mapping to? No, it's not 1. If I go from -1 to 1, what is the side? 2, right? Trick question. I also got confused, to be honest, when I was calculating the area. It's not matching. Remembered. 2 by 2. So the area is 4. And what is the area of this square in this example? So the area in this example is 3 by 3. So the area is 9. So it should be a ratio of the 2. The Jacobian scaling is scaling it, right? Because the square in this example is larger than the mapped regular thing that went from -1 to 1, right? The standard element, right? So it's scaling from that area to this one, right? In a lot of your situations, like your homework problems, all of these are populated with 1 minus C, 1 minus eta. You're going to have stuff here. I just chose elements for simplicity that will not have that situation, so I can explain to you the process, okay? You understand?
What's the vector C again?
The coordinates of the nodes. You can calculate, so for node 1, the coordinates are 0, 0. That's what the first pair is there. Second pair is 3, 0. The third pair is 3, 3, and the fourth pair is 0, 3. You can see those there. They're next to each other. Okay? Yeah? Any questions? Okay, so now I'm ready to calculate these derivatives that I'm going to need. I'm going to need these derivatives. So then I have to calculate Jacobian, which I did already. J inverse, I already have that. I have to calculate these derivatives. So for shape function 1, if you go back to the previous lecture, shape function 1 is 1/4 of 1 minus c, 1 plus 1 minus eta. So if you find that derivative and you multiply this column times that matrix, you get this equation. So I'm able to calculate these values. And I can do this for shape function 2. I have to do this for shape function 3 and 4. Okay? So I get this. Okay, so now I'm ready to calculate what B bold is. These are blocks. Remember I call them block 1, block 2, block 3, block 4. So I just expanded it out for you so you can see how it looks. And what I'm doing is putting the value there that I calculated in the previous page. Just populated that. Okay? So the C metric is fully known. I know it's aluminum, so it's 10 E6 PSI or 10 MSI. Poisson ratio is close to 2.3. So this is fully populated. These are just functions of eta and C. Plug all this in here. Take the transpose times C times B. Integrate from -1 to 1 using Gaussian quadrature. You guys know how to use that. I showed you in the previous lecture how to do that. The integration points, I believe, are plus minus 1 over square root of 3. I could be wrong. Something like that. And the weights are 1. So let's cover now this one here. If you recall, there's an N transpose here, remember? And I have the body force here, B bold. N transpose times B bold, remember? Because I have weight now. The body force is Bx. Do I have a gravity going in the axial direction? 0. I have going downwards, minus rho g, so that's this one here, By. And N transpose is this one right here. That's what N transpose is. We had N defined somewhere here, so that's N right here, N bold. So if you transpose that, that's what you see. I'm going to ignore this a little bit longer, but we can cover it a little bit now. So if you remember, I'm applying a surface traction, and I'm applying surface traction age 4, 5. You agree on element 2? 1? Yeah? So that's a surface integral that I had to calculate. If you remember, that was N transpose times traction, bold. So traction bold, you saw that in the previous picture, T bold only had components along the x direction. So that makes sense, tau 0. There's nothing going downwards. So traction in the y direction is 0. And then again, N transpose. And I have to integrate this now, but in the edge 4, 5. I have to focus on that edge alone. Okay. Unlike this one. This one has to be integrated over the area, over the whole thing, because it's the body force. Does the gravity only apply on the surface of a little structure? Gravity applies to the whole body, the volume, all its interior, right? So that's why this looks different from this one. Okay? Any questions? Any questions? We're going to cover this integral using the same approach as we used the heat transfer problem. I'll show you how to do it here in the solid mechanics. We'll cover this one more step later. So we're going to do it now. Let's do it now. So if I multiply that matrix times the gravity vector, this is what I get. And it makes sense because the element formulation for this guy should be 8 unknowns, right? Since I have a quadrilateral, how many unknowns I have? 4. So I have to have how many unknowns? 8. So it should be 8 in length this way. And this should be 8 by 8, whatever I get here. Okay, and then when I multiply this n times this traction, I get that vector here. Okay? Right? Now, remember, I'm only applying load on this edge, right? On that edge. And so, what was my connectivity? 1, 2, 4, 5. So I have to take this edge and map it to my square. And when I do that, that piece really acting on this connectivity, this edge, 3, 4, which maps into this edge, which is 3, 4. And so I have to evaluate this integral along this edge. You agree? Yeah? That edge is given, do you agree that this edge is given by eta equals 1? Right? So I have to evaluate this shape function matrix at eta equals 1. And not only that, now I have a differential element here that has to be evaluated. That differential element is deep C, and by chain rule you get this equation. I covered this with the heat transfer pump. Evaluate at eta equals 1. Okay? When you do that, you basically get the element formulation for this element, which is given here. Okay, so you evaluate eta equals 1, and then the square root, you evaluate eta equals 1, and then you basically get this here. And when you integrate this guy here, you get 0, 0, 0, tau 0, 0, tau 0, 0. Okay? And then you get 3/2 here. Okay? The question is, does this make any sense? What I got make any sense? And you can go back and check to make sure it makes sense. Okay? You agree that this represents for node 1? That's for node 2? That's for node 3 and 4. For node 3 and 4, it's only acting in the x direction. And what it did, Feynman's did, it multiplied 3 tau over 2 and 3 tau over 2 and put them in the x direction. Let's see if that makes sense. Let's go to the original problem. You agree that the length here is 3. I told you that. What is the total force on the top surface? 3 tau. So if I wanted to put some in here and some here, will I just divide it by 2? So 3 tau divided by 2, 3 tau divided by 2. That's a sanity check to make sure I did it correctly, right? And it also makes sense because it's only acting on the connectivity, so side 1, side 2, side 3. It's only acting on side 3, which is only joined by local node numbers 3 and 4. That makes sense, and that's what we see also here, what showed up here. It only acts in node 3 and 4, but only in the x direction. You guys get it? You buy into it? I don't want to promise anything. But if you integrated this here, I think what you're going to get is rho g, but distributed in the 4 nodes by 4. Because there's 4 nodes in the quadrilateral. So I think that integral, actually let's do 10.6 extra credit if you do it. Integrate that, I think you'll find that rho g, no?
What about the channel?
Sorry?
What about the channel?
Triangle. Well, we're just looking at quadrilateral so far. So for at the element level, you have a square, or whatever it is. If I do this integral, I think the code is going to put rho g of that element is going to divide it by by the node. So it would be rho g divided by 4. It also needs to consider the area. So the area of the square is about 9 times the thickness 1. So you can calculate the weight, and it will be putting a fourth of a weight each node. I think that's what it's going to do. Check it out. Tell me what you find. I'll be interested. All right. So now let's do the triangular element. Triangular element is this one here. Triangular element, I'm going to use the RNS coordinate system. And I've selected these to be the nodes, to be the first node, second node, and third node. I didn't select this one to the first node, second node, and third node. I just did it this way, okay? For the mapping purposes, so I can map that traction force a little bit easier. So then I have the coordinates of that first node, which is 6, 0. That's 3, 3, so that's 6, 0. And then second node is here, so this is 3, 3, so that's 3, 3, that location. And then 3, 0, which is this node here, third node. Okay, so that's the coordinates there. Shape functions times that gives me what I need to then calculate the Jacobian. And when you do that, you get that, J inverse is just that. I did it in that one I had to do with Mathematica. But the determinant is 9. Okay, 9. That's actually correct, because if you look at the triangular element, the standard triangular element, what is the area? 1/2. What is the area of this triangle? 3 by 3, 9. 9 divided by 2. So I'm mapping a 9/2 to 1/2. So the mapping is basically 9, the ratio of the two. Make sense? I went from an area of 9/2 to an area of 1/2. So the ratio is basically Jacobian. It's scaling in this case. Okay. In other cases where the elements are highly distorted, it's not going to scale that nicely, right? Then, once I have the Jacobian, I can also find the derivatives. If you remember from the previous lecture, shape function 1 was 1 minus r minus s, remember? So the derivative of that with respect to r is minus 1. And then you can calculate the derivatives, multiply all this, and you get very nice numbers actually. They're all numbers. I can plug this in now into B bold, and when I do that, this is what I get. I get a matrix of numbers. So that's why problem number 2 should be easier. You should have all numbers, I think. C bold is all known. B bold is all known, and that's why it's called a constant strain triangle, because it's just a number. The strain does not vary across the element because it's constant. Take that, substitute it here, and now I'm ready to go. The gravity is the same as before, okay, just like before. But my integrals now go from 0 to 1 minus s because it's a triangle, and 0 to 1. And then here, I have to be careful. So this is my traction forces now, which are acting on this surface. Okay? You agree that the traction acting in the x direction is basically tau 0 square root of 2 over 2 to the right. And then the traction acting downwards in the y direction is tau 0 square root 2 over 2. This is a 45-degree angle. This is 3 and this is 3. Of course, I chose numbers that are quick for me to implement. So therefore, that's why you see a tau 0 square root of 2, positive, and minus tau squared over 2 because it's going downwards. Okay. Now, so the mapping is being taken care of automatically by this process. I don't have to do a lot. And transpose is this. So just multiply these two together. When I do, I get this, and my guess is that when you get the integral of this, you're going to get rho g times the area of the triangle, and it's going to put a third of that load on each node, equivalently. We're going to now look at this one here. So this one here, I put the square root over 2 here, because I had tau 0 divided by square root of 2. But in essence, this is what you have. This has to be evaluated on what edge? On this edge, right? This edge is 3, 4. But this edge corresponds to what edge on the mapping? On the mapped coordinates, the standard element? 1, 2. Because I started with this one in my connectivity. I started as 1, 2, 3 for the local number. So if you go back to the connectivity, I'm looking at the first edge. In that first edge, S is 0. You agree? I'll use the board for the first time in this class. That's R, that's S, that's R. We're on this edge right now, because the local node number is 1, 2, and 3. Here on this edge, S is 0. When you do that, things simplify a little bit. This shape function simplify a little bit, and you get these two to be 0. That makes sense because node number 3 is not involved in any way on what's going on in this edge, right? So automatically finite elements is capturing that. Also, when you calculate this square root, when you calculate x and y, what you'll find is that you get the length, okay, of this edge, of the edge here. Automatically you get the length of this edge, which is 3 over square root of 2. 3 times square root of 2. So when you do it mathematically, it's going to come out to be this, okay? So from there, now the integral from 0 to 1 is easy. I actually did that by hand. And what you get is 3 tau 0 divided by 2, 3 tau 0 divided by 2. Okay? So let's see if this makes sense. Let's see if this makes sense. We can check that. Okay, this length is 3 square root of 2. Agree? So the total force in that surface is 3 square root of 2 times tau naught, right? We'll take half and put it here, and half put it there. But now I have to take that force, which is along here, and I have to decompose it into x and y. And when I do that, I'll get 3 half tau 0 on each direction. Okay? Any questions? Yeah? Do it at home. Check it at home. I didn't give you all the steps today. It takes a lot of time, right? But you can work it out at home. The next step, I didn't complete it, but you will assemble the stiffness matrices. You'll assemble the load vectors now that you have them. You'll use the connectivity matrix to do that. You'll apply the boundary conditions, which was fixed on the left-hand side. Then you'll solve for displacements. Once I know the displacements, I get the strains. Once I know the strains, I can get the stresses using this formula. I know the B matrix. I know the nodal values, so I can calculate the stresses. These stresses are typically calculated at the integration points, Gauss integration points. That's how you calculate this. Because remember, B bold depends on C and eta, right? Or R and S. And so for that reason, you evaluate these at the Gaussian points. And so if you went to Abaqus and queried an element, the values of the stresses for an element is going to give you, if it's 4 integration points, it's going to give you 4 values. And those 4 values represent the values at the integration points. Okay? So this is how you calculate stresses. Once you know stresses, you can now calculate the von Mises stress to predict failure of metal, or you can use a failure criteria of your choice if it's composites, right? Or max principal stress if it's a brittle material, and so forth. I will not cover that here, but if you go to the mechanics materials book, it will give you the formulas there for von Mises and max principal. Once you know the stress vector fully, okay? But you can come back at the end and I can show you the formulas. Okay. Some notes, I'm not done yet, just give me a few more minutes. Some notes now that I want to cover really quick is that if I were to take a triangular element and use them to, and thank you Leonardo for this, if I took triangular elements and I mesh this and I apply loading, I'll have oscillations that occur that go from positive to negative back and forth. And if I had a single element, it would be even worse. You'll see that in your homework because your homework was done on purpose so you can get something like that, positive, negative. Why is that happening? Physically, why that's happening is because in the triangular element, linear triangular element, the strains are constant. Because the strain is constant, do you agree that if I apply a load here, it wants to bend that way, going up, right? So I'm applying bending, so the thing wants to bend upwards. You agree that the top will be in compression, the bottom will be in tension, right? So you agree that this is in compression here? Yeah? So if it's in compression, and since the strains are constant in the element, then all these elements will have a constant compression value, right? The bottom element here is in tension. The bottom edge is going to sense that it's in tension. So now this whole element will be positive tension. This whole element will be positive compression. You go positive, negative, which is what you're seeing here, but at a less extent because we're using more elements through a thickness. Does that make sense? So this behavior actually results in an undesirably stiff behavior and produces very low, very, very slow convergence. It cannot represent pure bending very well, and so you'll get this issue, this locking issue. You'll also get locking issue there. The linear quadrilateral element for single element across Q4 will behave a little bit stiff also. And the reason for that is because of the bilinear displacement field that we have chosen does not allow you to represent curvature very well. Okay, it only allows you to basically model this kind of situation. Does not allow you to model this situation. So for that reason, you're going to also have an overly stiff behavior, and you're going to have some amount of shear locking in this type of element. But it works better, as you can see already just by looking at it, looks better than the constant strain triangle. And look at the value here, it's 4.49 E7 stress in the bottom fibers. If I go here to Q8 element, which is actually going to be close to the exact solution, it's 6.029 E7. So this, just a single row of elements, Q8 did very well. In fact, it almost matches the exact solution. The linear strain triangle, which is a second order element, is a trias 6. So 6 nodes, triangular element, quadratic interpolation, very nice as well. You can see here it gives you 6.19. These two are very close to the exact solution, E7, 6.19 E7. Q4, and now it's Q4, but now let's add an extra row, just for fun, of elements. Even this one is still stiff, 5.8 E7. Still not as good. If you want to get a good behavior with Q4, use at least 3 elements per thickness to model bending very well. This is a constant triangular element. Don't want to even cover. That's about half the stress. So even talking about it is a waste of time. If you want to use a look at tip deflection and compare the different element types, you guys already know what reduced integration means. I'll cover that a little bit later as it applies to solid mechanics. But you already guys know what to do with reduced integration, basically using less integration points to evaluate the integrals. When I do that, the error compared to the exact solution, really, really stiff for triad 3, just a triangular element, linear triangular element. For quadrilateral element, 11% stiffer than the exact solution, much better. Reduced, too flexible. And then when I go to second order, all of them look really good. I mean, that's the percentage error there. Really good. Second order basically takes care of a lot of headaches, but then it comes with computational expense. Second order elements in general, these are examples of second order elements for 3D and then for 2D. But strains are fully linear in all directions, so you're going to have a very well, it's going to capture bending very well. Very accurate without having to use reduced integration. Computationally expensive because you have more degrees of freedom, obviously. Mesh refinements. You can refine your mesh, and if you refine your mesh by increasing the number of elements, you're going to reduce the element size. We call this mesh refinement H refinement. H refinement because we're reducing the characteristic element size. We're making it smaller. And so that's what we call this H refinement. P refinement is a situation where I say, okay, I don't want to increase the number of elements. I'm going to go from linear elements to quadratic elements. Suddenly, I have a better solution, right? I'm going to increase the accuracy of the solution. And that alone is called P refinement. And in this case, what we're talking about here is that we've increased the order of polynomial to describe the interpolation functions. Any questions on this before I continue to? I have only a few more slides, if you don't mind. Okay? Any questions on this? So there's two types of refinements, H refinement and P refinement. So element checks. Element checks are very important. These came from Hypermesh. These are their standard numbers that they provide you for element checks to make sure they're of good quality. So distortion of the elements will generally introduce error in the solution. The Jacobian calculation usually will use quadrature, and so you will have it will be inexact. So the better approach is to have elements that are regular in size, as regular as you can to the standard element. And aspect ratios can result in stiff behavior, and then you definitely don't want to have excessive distortion, warpage, or curvature. And I here give you examples of different things you could have. And these are checks in Abaqus, in Hypermesh. They're meant to prevent and safeguard those finite element models from being inaccurate. So one of the reasons is because the Jacobian is extremely, if you have a highly distorted element, your Jacobian is going to be troublesome in value. Okay, so you want something that's not. Okay, we can take advantage of making everything look the same, but you don't want to take too much advantage to the point where you've reduced the benefit of it. And so that's what we're talking about here. A few more points here. You can use incompatible mesh. You can. So I've used it in an example here at the bottom. I gave you the paper I wrote. But in this example, our area of concern was composite failure at the hull. Well, I don't need to have a refined mesh here. I don't need a refined mesh here. I can use a coarse mesh here, a refined mesh there, and just focus my answer there, right? So that works very well. In Abaqus, you can use a tie. It allows you to tie the edge from this mesh to the edge of this mesh. Allows you to tie those together so the solution can proceed very nicely, so that it doesn't do that versus this, okay? So we want to have this behavior, not that behavior, unless you want to put a crack on purpose. Then in that case, I think you can do that. Incompatible meshes can be used. Nastran uses glue. Is that correct? You probably know. He probably uses very nice transitions. He goes from coarse mesh to fine mesh and has very nice transitions. But now you have glue command, and you can now have coarse areas. And let's say 80% of the structure in the area that you think is going to fail, just put fine mesh. It will save you computational time. That's what I do now. Also, it's important to check that once you mesh everything, they have coincident nodes. There's sometimes nodes, you can have elements that are disconnected. So you can actually equivalence the nodes to make sure that everything is glued together. You don't have nodes floating around, okay? So you want to make those checks with your models, okay? That was my final chart. This was just more practical aspects of finite elements. I'll cover some more later. But this is related to 2D and 3D, so that's why I wanted to cover it here. If you have any questions, don't hesitate to stop by here, okay? I'll be here